Hello, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell. I work at deepastronomy.com, and boy, am I excited about today's hangout. We're going to be talking about dark galaxies or diffuse galaxies, and in particular, we're going to be talking about a galaxy called Dragonfly 44, which astronomers have observed using an array that is called the Dragonfly Telephoto Array, and we're going to be talking about what that is as well, and all kinds of fun things. So we're very excited about today's hangout, and I'm also excited because we have our very first hangout sponsor today. This hangout is sponsored by the Dot Space Domains Group. The hangout, the link to what they have there is down in the description box below. It's also on our website, and these guys are the registrar for the Dot Space Domain web space. And so if you are an amateur astronomer, if you're a professional astronomer, somebody who is looking to make a name for themselves on the web, and you want to improve your visibility, then a dot space domain would be a great way to do that. I just did the Deep Astronomy .space registration a couple of days ago, so I got that name, and now I'm going to be using it for more stuff for the Deep Astronomy content. So please check it out. The link is down in the description box below of the video. If you're watching it live, it's also on deepastronomy.com/live, where you can also get a discount on the first year of registration. So please check them out. And I want to thank you guys. I want to thank Dot Space Domains for being our very first Hangout sponsor. Okay. Also, I should point out, and I want to mention that these Hangouts are endorsed by two American astronomical or American societies. First, the American Astronomical Society and the American Astronautical Society. They use these Hangouts so that we may highlight the science and work being done by their memberships. And so we want to thank them also for their endorsements. And while I just need to say that while the opinions and while the Hangouts are endorsed by both AASs, the opinions expressed here within these Hangouts are not necessarily endorsed by those organizations. So without any more ado, let me just get started. And first off, I got to introduce my colleague, Dr. Carol Christian. She's my co-host. Hi, Carol. How are you doing?
Hey, I'm good. I'm really excited about this hangout. I was really captivated by this story.
Dark galaxies, I know.
Dark galaxies, yes. And so, yes, I'm very excited about this, and I'm glad to be here.
Yes, and so it'll be a really interesting hangout, I think. And so let me introduce our guests. Joining me is Dr. Pieter van Dokkum. He is the Saul Goodman Professor at the Yale University and one of the authors on the paper that we're going to be talking about today. Hi, Peter, and welcome to our hangout.
Yeah, thanks for having me.
Also joining me is Dr. Roberto Abraham. He's from the Department of Astronomy Department at the University of Toronto, and he's also the president of the Canadian Astronomical Society. Hi, Roberto, welcome.
Hey, Tony, thanks for inviting me.
Oh, you're very welcome. I'm excited to talk today. Couple things. This is a hangout on air. We want you to interact with our guests. You can leave questions and comments. There are two great ways to do that. One of them is by going to deepastronomy.com/live and joining our live chat there. We already have Andrew Planets here asking questions, which I will get to, Andrew, and it's good to see you back. I'm glad you're back. And I guess you were able to work out your time scheduling conflict, so thank you for joining us. Also, if you use the hashtag AstroCoffee, you will be able to ask our guest questions. I'm monitoring that on my tweet deck, so please do that as well. I also have the live chat going on the watch page on YouTube, but I'm not going to be paying as much attention to that as I do the live chat on the Deep Astronomy page because of a lot of reasons. So anyway, okay, so Dragonfly 44 is a galaxy that was observed by our guests here today, and it was determined that it is, after a lot of very painstaking observations and using very unique equipment, they were able to determine that it's a galaxy that's made up almost entirely of dark matter. So I think what I'd like to do is start with you, Peter, and give us a little background on the galaxy itself, and then we'll talk a little bit about how you observed it. So can you tell us, what is Dragonfly 44?
Yeah, it's a galaxy in a particular class of galaxies that we discovered 2 years ago with this Dragonfly Telephoto Array that we built in New Mexico. And they're galaxies that we didn't really know existed in any large numbers in the universe before. So it was very exciting to discover this new class of objects. And basically, they're very big. They're as big as the Milky Way and sometimes even bigger. But they have very few stars. So they have like 100 or 1,000 times less stars than the Milky Way does, even though they have the same size as the Milky Way. And when we discovered them, we already suspected that something must be keeping those galaxies together. Essentially, what you expect is that because they're so diffuse, they have so few stars that they would be easily ripped apart, soon after they formed. But just the fact that they exist, and particularly where we found them in a cluster of galaxies, suggested to us that something is keeping them together. So we already suspected when we found them that they might have a lot of unseen matter. And then, we did all this painstaking work, indeed, and we went to the Keck Telescope in Hawaii and spent an incredible amount of time observing this one galaxy in particular, Dragonfly 44, and then found out that yes, indeed, it is mostly made of dark, and the stars are just a little sprinkling on top, basically, of this remarkable object.
I have a picture of it up here, and looking at this galaxy, it looks like there's not a whole lot of structure to it. This is one of a class of galaxies that I guess you guys are calling diffuse galaxies, right?
Yeah, they're basically blobs. They don't have much structure. They don't have these nice spiral arms that the Milky Way has, and it's like if you threw a galaxy in a blender and you would turn it on for a while, then this is what you might see. There really isn't much structure to them. We've looked, also with the Hubble Space Telescope, and they're just big, splotches in astronomical images.
This is yet another case of why astronomers have such difficulty naming things, because whatever they think comes out of their mouths. And so blob galaxy probably wouldn't, be very popular, but diffuse galaxy is pretty
well, astronomy's full of blobs, isn't it? And there's only so many ways you can say a blob, right? So here's a good graphic of what we're talking about. You'll see
it's beautiful.
On the left, you'll see a very nicely detailed picture of the Andromeda Galaxy, which is our neighboring spiral galaxy. And you also see an elliptical dwarf galaxy in there, which is one of the satellite galaxies of M31. And off to the right is this insert of an ultra diffuse galaxy. So on the one hand, you have Andromeda, which is beautiful, lots of structure, lots of dark lanes, lots of stars and whatnot. Then you have a dwarf galaxy, very blobbish. I mean, I'm looking at it, it looks pretty blobby to me. And then we have this ultra diffuse galaxy here, which is sort of, it's not Dragonfly 44, is it? This is another one?
Yeah, this is Dragonfly 17, as it happens.
Okay, good. Well, we're going to talk about what Dragonfly means in a minute, but So Roberto, what do you have? Do you have anything to add to what we're talking about here with these diffuse galaxies and these classes of galaxies?
Maybe the only thing I could add is that a lot of that credit for this really goes to Peter's eyeballs.
Whose eyeballs?
Yeah, his eyeballs.
Astronomers don't use those anymore. We use computers.
Well, apparently some of them do, because people have been looking at the Coma Cluster for 100 years. Peter took a look at our Dragonfly observations of this cluster and instantaneously saw that something was amiss. So I feel a lot of the credit for this, does indeed go to the technology, but part of the story that should not be missed out was I think Peter is unusually competent when it comes to looking at images, and his spider sense sort of tingled that something was going on here, and instantly saw that there was this population of objects that just
so he has
shouldn't be there.
So could it be said he has a really strong blobdar then? He can really...
I think his blobdar is unparalleled.
You've heard it here first, folks. Blobdar. It's going to be a new job skill for astronomers in the future. Yeah. Well, I want to talk about how you got to that in a minute, Peter. But let's go to maybe let me just show this again, because I want to talk about where you guys looked. You looked in the Coma Cluster, which was located in the constellation Coma Berenices right here. It's a little cluster. Oh, I'm pointing to the wrong thing. It's a little cluster right here. And how far away is Dragonfly 44? Can you guys tell us? This is not within our galaxy, correct? It's in another cluster of galaxies.
Yeah, that's right. It's in the Coma Cluster, right? So
Yeah.
it's like 100 megaparsecs out.
Okay, so it's very far away, and it's not exactly all that distinct. So you look at the Coma Cluster, Peter, and according to Roberto, you just see something amiss. You want to comment a little further on that? What does he mean by that? You're just looking at images, by the way, on your computer screen.
Yeah, we were both at a meeting in England, in Oxford, and during one of the talks, I started looking at this image that we had taken, and of course, you're supposed to pay attention to the talks, which I'm sure I did as well. But
yeah, right.
laptop was open. What are you going to do? And yeah, there were just these little fuzzy things in the image, and now, with most telescopes, if you see little fuzzy things that shouldn't be there, it's because there's some artifact in the images. They could be ghosts of stars, or some
internal reflections, things like that.
Yeah, exactly. It could be the moon glinting off of some support structure and back in your image. All sorts of reasons why little faint fuzzy things are not sort of real and not actual astronomical images. But the nice thing about this Dragonfly array that we used is that it almost has no such artifacts in the processed data. The images are incredibly clean, and they're especially tailored for low surface brightness emission, so this extended diffuse emission in the night sky. And so both sort of, because we were looking for those kinds of things, low surface brightness objects, and the fact that these images were so clean meant that I was sort of primed for these things and took them seriously. I think
so. Carol has an image of this up, and so are these the kinds of images you were looking at then?
Well, this image that was taken that was up was taken with the Gemini telescope afterwards. So the initial images were of much, the Dragonfly pixels are quite big, and so the galaxy only subtended a few pixels in those images that were taken with Dragonfly. And it's also another part of this story is sort of sociological. As Bob said, there's been a lot of people with a lot of telescopes looking at the Coma Cluster, and yet they miss these objects. But after we found them, people went back and looked in archival data taken with the Subaru telescope in Hawaii and with the CFHT telescope, and then quickly found not tens, not 20s, but thousands of these things literally in all sorts of galaxy clusters. So there was a flurry of papers after our discovery paper which says, oh yeah, actually we see them too in our data. But people had seen them but just didn't know they were real objects, or they were not primed to think that such galaxies could exist. Because everybody knew, that low surface brightness things, these little low surface brightness blobs, were nearby dwarf galaxies or artifacts or something like that, but would not be Milky Way-sized objects at the distance of the Coma Cluster.
And that's the real thing here about these this galaxy type, is that these are very dim, very diffuse, yet they're huge. And when you say big, do you mean physically big, or do you mean massive? Like it compares to the mass of our Milky Way, or are they physically the same size?
Yeah, thanks for making me be specific about that. What we know, what we can measure easily, is that they're physically big. So they have a large spatial extent. Now, measuring how massive they are is a much, much harder proposition. And so we've only done that for a few of these things, and particularly this Dragonfly 44, because that required measuring the motions of the stars in the galaxy. And because they're so dim, they have very few stars, relatively speaking, and it makes it very hard to get enough signal, even with very big telescopes, to measure the motions of the stars. So that was very difficult to do that part. But yeah, when I say big, I typically mean physical size.
And that's how dark matter has been discovered, is by measuring the motions, either within one galaxy or galaxies relative to each other. So you can't just take a picture and say, aha, oh, there's dark matter. We have to actually measure the motions of the objects. And that can be very time consuming, and you need a big telescope with a great spectrograph on it in order to do that.
So there's a trick, of course, right? Which is Carol will like, which is, if you look at that picture that was just displayed of Dragonfly 44, you see.
I have it up.
Yeah. So what do you think those little? So you got the big blob and the little blobs inside the big blob.
Oh,
what do you think those are? I think Carol might know.
Are they
Carol, wait your turn. Okay, Carol, go ahead. What do you think it is?
Maybe they're globular clusters. Those are clusters of stars that have many, 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 many stars, and they are formed around big galaxies.
Right.
Did I get right?
You get an A+.
Okay, but wait a minute here. So I'm a little bit confused, because when I read the press release from Keck, I thought that the reason, so you said it's physically large, Peter, but it's also roughly comparable in mass to our Milky Way, right? The same, like hundreds of billions or trillions of solar masses in size, right? So so they're both.
For the general class of these objects, we typically only are able to measure the size. For this particular galaxy, Dragonfly 44, we've also measured the mass with the Keck Telescope with great difficulty. And so then it turned out that the mass of the galaxy was also similar to that of the Milky Way. Now, there's a big uncertainty in that, because it requires extrapolating from the part that we can actually measure the mass to the entire dark matter halo, which is much larger than that little image that you showed. So there is an uncertainty associated with this measurement, but our best estimate for the total mass of this object is about the same mass as the Milky Way, about 1 trillion solar masses.
So you have this galaxy, very dim, it's physically large, but it's also extremely massive. And you know that it's massive because you took some painstaking measurements of the motions within the stars. I want to talk about that a little bit. You guys make the claim about these diffuse and dark galaxies, that they are primarily made of dark matter. What evidence do you have to support that?
Well, you can calculate what the motions of the stars would be if there was no dark matter, if there was only the stars in these galaxies. And then you would expect to measure a velocity of the stars of about 7 kilometers per second. Okay, that is it's fast, but actually pretty slow as far as the motions of stars.
Based on the stars you could see, that's what you would expect.
Based on the stars that you could see, that's what you would measure. And so we went to the Keck Telescope, did the measurements using the Doppler effect. We measured the mean motions of the stars in this particular galaxy, and we measured the velocity of about 50 kilometers per second.
Much faster.
So much higher than what you would expect based on the stars alone. And so that difference is then caused by some additional mass.
Something you can't see.
That we can't see. So the idea that it's dark matter that's causing it, that is based on the other galaxies where we the general problem of missing mass in the universe. We don't know actually what the missing mass is, but that's a general problem. So we ascribe it to dark matter. That's what astronomers do when they find mass, that shouldn't be there. So that led to, and that then leads to an estimate of the amount of mass, in the region where we see the stars, the amount of mass that's there, and then we can compare that to the amount of stars that are there, and that gives us an estimate of the total amount of dark matter.
Okay, so that's an important point. Here, I have a graphic that I took from the European Southern Observatory's website that sort of shows the Milky Way with the large and small Magellanic Clouds in here, but also there's this big halo around it. This is what you mentioned earlier. This is a artist's representation of a dark matter halo around the Milky Way, and it is much, much larger than the galaxy itself. It even encompasses our nearby neighboring galaxies. Is the halo that you suspect, would you suspect a similar kind of arrangement in Dragonfly 44, or would the dark matter be arranged differently, or do you just not know based on your observations?
Well, based on my observations, I mean, yes, we assume that it's distributed similarly in the sense that it's much, much larger than the galaxy that we can see. But we'd love to know, of course, whether that's actually the case. And we have some hope to use the globular clusters that Bob mentioned, which have a larger spatial extent than the stars. Maybe with the James Webb Space Telescope, we might be able to measure the motions of those things and to probe the mass a little further out than we have done so far. But yeah, we basically measure the mass inside where we can see it, where we can see the stars, which are then the tracers of the mass, of how much mass there is. And then we say, well, if this galaxy has a dark matter halo, like other galaxies, then the mass of that dark matter halo is 10 to the 12, trillion times the mass of the sun. But we don't know that part for sure. We only know for sure what's inside the galaxy, in the part that's on your picture is within that sort of yellow ring.
Okay, well, I just want to interrupt for just a quick second here and remind everybody that you are watching the Astro Coffee Hangout that is endorsed both by the American Astronomical Society and the American Astronautical Society. And we also have our sponsor from the Dot Space Domain Group. If you are interested in getting your name out there, carving away some of your astronomical real estate on the internet, this is a good time to do it because the Dot Space Domain is pretty brand new. You can get some great names on there, and if you click on the link in the description box here, you'll get sent, and you'll also get a deal for the first year of membership, or for the first year of registration of your domain name. So check it out. It's good for people in the space industry, as well as amateur astronomers, astronomers looking to make a blog for themselves, all kinds of things. So please check it out. And so what we are talking.
I will have a question when you finish your reintroduction.
Okay, good. So we are talking with members of the team who discovered Dragonfly 44, who has studied Dragonfly 44, a dark galaxy, a galaxy made up of 99.9% dark matter. And joining me is Dr. Pieter van Dokkum. He's a professor. He's a Saul Goodman professor at Yale University. Also, Dr. Roberto Abraham from the Department of Astronomy at University of Toronto, and the president of the Canadian Astronomical Society. And Carol, you have a question.
I do. So we're talking about the specific locale of this galaxy, Dragonfly 44, and you're measuring the environment there, and you will measure things that are further out to get a mass estimate. Is there much known about the mass distribution in the Coma Cluster and the peculiar motions within the Coma Cluster, or is that a pretty big question and needs lots of observations, or how does that work? Or mostly people looking at the individual galaxies in Coma Cluster?
Well, I mean, the Coma Cluster is incredibly massive, and so that's the first thing to note, right? Even amongst the whole panoply of clusters in the universe, Coma stands out as being way at the high mass end, and it's also relatively messed up. So it's certainly not the environment that you would have suspected would be one that would be friendly to these giant low surface brightness galaxies. Sort of the last place that you would think to look for such things. So I think part of the most interesting part of the story here is that we did not find these things in the middle of nowhere in the field, a fairly gentle environment where you could envision these big things might survive. Instead, they were found, in this case, sort of in the outskirts of this really hostile environment for things. If you drop a galaxy into something like that Coma Cluster, it's going to be subjected to these incredible tides. The observations with Keck that indicated that this thing has a lot of dark matter, and the observation of these large number of globular clusters, which also suggests that its mass is large. It's sort of consistent, I think, with the basic observation that these things exist at all, right? So unless this is making its first pass through the cluster, which I guess is possible. Just keeping the thing together, would require a lot of dark matter. So that's sort of a third. There's sort of three things I think that suggests that that dark matter content of these is very high, and I think that's the last one. The fact that its environment is one where it should be getting pulled apart unless it's got a lot of matter that you're not seeing that's holding it together.
So so you guys mentioned that one of the telltale signs of having a lot of dark matter is also the motions within the star. So you're saying that this galaxy is in a cluster where it should be getting ripped apart and it isn't. So something is holding it together. The motions of the stars are on order of, what did you say, 50 kilometers per second? Is that what you said?
Yeah.
Kilometers per second. And you expected something much, much lower. So that was another telltale sign. Now we're talking about measuring star motions in a galaxy that is megaparsecs away. Now, when I grew up, I was taught about how the universe is a static place, how everything doesn't change all that much. But you guys are actually looking at the motions of stars within the galaxies. How long does that take? You can't just take a snapshot. You've got to get a movie of these things, right?
It's not. That's not quite what you need to do. You don't have to actually watch the stars move, in the sky, which helps a lot, because that would take millions of years to actually see that kind of effect on the sky. Luckily, we can use a trick, and that is that the motions of the stars are also imprinted in the spectrum of the galaxy. And the spectrum has all these absorption and emission lines, particular wavelengths. Light is emitted and absorbed. And then that causes lines that are intrinsically very narrow in the spectrum. So you have at a particular wavelength of light, you have a little peak or a little dip that's intrinsically very narrow. But due to the motions of the stars, of all the individual stars in the galaxy, those lines get broadened. So stars that are coming towards you have a velocity towards us, and they'll cause the line of that individual star to be a little bluer, and stars that move away from you cause the line to be a little bit redder. And the combination of all those thousands and of stars in that galaxy cause those lines to be not very narrow, but broader.
So
with these absorption lines in the spectrum tells you how fast the stars are moving.
So we've talked a lot about redshift of galaxies, and we know about this shifting of lines, absorption lines in a spectrum to know whether it's going, the entire galaxy is going towards us or away from us. But you're talking about if you took a spectra of Dragonfly 44, the individual stars within it, their spectra will be either redshifted or blue shifted depending on their motions within the galaxy, right?
Exactly.
And that's how you're getting that. And you can do that with one photo or one spectrum?
Yep, because those stars are on,
well, that's nice.
They are moving, and they have that particular imprint, even if you just take one spectrum of that galaxy. Now, that doesn't mean it's easy, because the light is so faint of these galaxies. So we had to use the Keck Telescope on 6 nights for a total time of 33.5 hours. So we looked for 33.5 hours at this same object, which is one of the longest exposures I think ever done with.
Well, it's also made worse because spectra take longer to make than the normal image too. On top of it, right?
Yeah, exactly. Because you're spreading the light out in wavelength, and so for each wavelength you need to integrate longer. So we use the largest telescope on Earth for some of the longest exposures that it's ever done to make this measurement. Okay,
now I want to talk about why it's called Dragonfly 44. This is what.
Wait.
Hang on.
Just, if you can just look at my screen.
A science lesson for us.
Science lesson. So it's what they were talking about. So you have, in this example, there's a spiral galaxy on the right, and because of the way the galaxy is rotating, you have stars that are blue shifted because they're coming towards the observer, and other objects that are stars in the galaxy that are moving away and they're red shifted, and then the ones in the middle aren't. But if you're looking at a whole galaxy at once in your spectrograph because it's far away and the light is faint, you get the aggregate of that. So you get the blue ones and the blue shifted ones the normal frequency ones, or that show up where they're supposed to, and then the redshifted, and it's all smooshed together, another technical term, smooshed together, and you get broadening of the line. Whereas if you could resolve an individual star, you would see it as blue shifted or red shifted, but when you put them all together, you get all of them together, and so they're all smooshed together, and the line is broad. And so you say, how wide is it? You measure that, and then you say, aha, that's caused by the motions of a whole bunch of stars due to the gravity attracting those stars. Voila, the mass.
Yeah, that's perfect.
It never ceases to amaze me how great spectra are in helping people, astronomers, figure things out from far away. That's just amazing. Great. Okay.
Okay.
I think that though is the picture Carol's showing is for a rotating galaxy, and in the case of Dragonfly 44, there's no evidence of rotation, right? So the individual stars are moving on kind of random orbits, but they get broadened out. But it's not the bulk motion of the stars that is causing the line to get broader. It's these random motions.
Yeah, well, sorry. In a pinch, that's what I can.
No, but that's a good illustration. Rotation is one way. It's a more structured motion.
It's going every which way, yeah.
Yeah.
Okay. So tell me about how you took this. What is this thing that we're looking at here? I want to talk about Dragonfly, the Dragonfly Telephoto Array.
That's the half of Dragonfly at the moment.
It's twice this large.
Yes. Yeah, we've got another. Right now, Dragonfly is 48 lenses, and you see 24 there. And that's so there's in a dome right next to this one. There's another identical array, and even more important than the array are the people. And so you can see me and Peter there, and also this crack team of graduate students that really have made this whole thing possible.
They always do. It's always great. Okay, so is this off-the-shelf equipment?
Yeah.
Are these telephoto? These are lenses, right? These are all.
Yeah. Peter, you want to describe it, or you want me to do it?
Go ahead.
Yeah. Okay. So the origin story for Dragonfly is humorous, and I probably won't relate it all here. But these are the king of telephoto lenses. These commercial, Canon telephoto lenses that have these wonderful coatings, these special nanostructure coatings, and so each of those is a 400 millimeter f2.8 lens, and they're not inexpensive. I think I haven't priced them on Amazon recently, but they're a little north of $10,000 each, and they are truly wonderful lenses. I can't believe, frankly, how good they are. A lot of the success of this project gets down to the quality of these things and the terrific job that Canon Corporation did in designing and building them. So individually, they're spectacular, and if you combine them in this way, effectively, what you're doing is you're building a much bigger telephoto lens by combining the images from all of them at the same time. So each of these is pointed at the same part of the sky, and each of them is feeding astronomical CCD camera, so a cooled CCD camera, and the images are taken simultaneously, and then they're all combined digitally, and the whole thing is commercial. The lenses are commercial. They're held on a wonderful fork mount that is also commercially available, and it's manufactured by this company in Colorado, Software Bisque.
Oh yeah, I know them. Mm-hmm.
Yeah, so they did a great job with these, and I think their commercial introduction was largely spurred by our need for them, and now they're selling them commercially, which makes me happy. They did us a really good turn with producing these things, and now the whole world can see how great they are.
Okay, now I came from I'm an amateur astronomer. I came from the time when I remember spending hours just trying to align my finder scope with the primary mirror. How in the heck did you guys align these all up, and how are they? Is every field of view adjacent to another, or is it all converging on one field of view? How are they aligned?
Yeah, so they're aligned onto the same position in the sky, more or less. You know, they're
So
not.
let me just back up. Each telescope is pointing at the, like if you had a star in the center of one, that same star will be in the center of all the others.
Yeah, to within, you know, 20 or 30 pixels. And the reason, you know, that, you know, this thing came together in the smooth way it did, largely gets down to the people in New Mexico who, you know, put it together with us in this just incredibly professional and skilled way. So we need to shout out to them. And so this is you know, a commercial outfit called New Mexico Skies Observatory. It's run by Mike and Lynn Rice, and his team out there are just spectacular. And so they, you know, so we hold these things in these machined cells that mean that they're vaguely pointed in the right direction. And then Mike and his team, you know, align them with much greater precision. You know, it doesn't take that long. It takes them, you know, a night or so, and they can get these things perfectly well aligned because they're, you know, so skilled at this thing. They operate many telescopes down there. So, you know, this seemingly super formidable task of operating the Dragonflies is something that they can handle.
So each tube or each lens is adjustable. And do they have to do that every night? Do you imagine because of flexure or anything like that?
No, the whole thing's pretty solid. So you know, they line them up once, and then it's good to go. The whole thing is you know, robotically operated using some software that, you know, we wrote, and it's, to be honest, it's just trivial to use, right? People look at it and they're like, "Wow, this must be highly complicated." And you know, when we were starting out and didn't really know what we were doing things in various dumb ways. It was much more complicated than it needed to be, but now it's like completely trivial, right? They're all pointed at the same place. You know, you instruct the, you know, Dragonfly to point at one position in the sky, and both arrays are you know, seamlessly do that. You just instruct it to take an integration. It takes an integration. The data gets stored reliably. It's all you know, the mounts are so good we don't need to guide. So it's really you know, painless to use. The grad students you see here basically you know, edit a script in the afternoon. They set it going, and then a Dragonfly does its thing. It kind of adapts. You know, we put some sort of low-level AI into this thing. So if it senses that, you know, clouds have rolled in, it does the appropriate thing. If the lenses, you know, the focus starts getting soft, it automatically refocuses itself, and you basically don't have to worry about it. So you just edit the script, set it going in the afternoon, and get your data the next day.
Where's the spectrograph?
There is no spectrograph. So this takes pictures, right?
Right, but how'd you get the motions of the stars then?
That was done with Keck.
Oh, okay. So this took a visual image of the galaxy.
Yeah.
Got it.
So, and that's, you know, that's, I think, a really important point to make, right? Which is that, you know, Dragonfly is part of an ecosystem of instruments that you use to try and learn stuff. What Dragonfly can do is, you know, identify objects in the sky that you then will follow up with, you know, Keck or Gemini or with Hubble. But you know, it's you know, position in this ecosystem is to find stuff, but to actually, you know, figure out what these things represent requires, you know, big telescopes and spectrometers, and that's just the way things work in astronomy, right? Taking pictures of things, you know, in some domains is all you need to do, but in general, what you do is, you know, you locate things, and, you know, you can understand some, you know, some important things from just their appearance. But ultimately, if you want to get physics out of things, you require the larger telescopes with the spectrometers. So they work kind of synergistically together.
And here's a picture of Keck, and I don't have one of Gemini North, but here's a picture of Keck that I presumably did have the spectrograph on it then, correct?
Yep.
Okay, so you know what this reminds me of? This reminds me of the early days of exoplanets. When I remember a guy named Dr. Tim Brown, who worked at the High Altitude Observatory, had a Meade 16-inch telescope sitting out in the parking lot of the High Altitude Observatory, and he was looking at tiny dips in brightness of a star. Found one of the first exoplanets by the transit method. And so that's from humble beginnings came, you know, I'm not saying he invented the the science. He didn't, but he was one of the first people to make these
Yeah.
observations with humble equipment. And this is not humble equipment. This is like, you know, I don't think I'm going to go out and buy all of those lenses. What did you say? How many are there altogether? 40 something, 50 something lenses?
48 at the moment.
48. So yeah, 10 grand a piece. No, I don't think so. But it is good to know that if you wanted to, you go to Amazon and make their day by ordering one of these Dragonfly systems. Okay, so I'm going to get to some questions and comments. I just want to say real quickly that this is an Astro Coffee Hangout. My name is Tony Darnell, and we are talking with Dr. Pieter van Dokkum from he's the Solomon professor at the Yale University. Also talking to Dr. Roberto Abraham from the Department of Astronomy at the University of Toronto and the president of the Canadian Astronomical Society. Our sponsor is the Dot Space Domain Group. They have space. They have the Dot Space domain names. If you want to start an astronomy blog or any kind of astronomy site, you need to get one of these because they're really cool. And if you click on the link, you'll get a discount for the first year of registration. So I'm here with my colleague, Dr. Carol Christian, and we're also we're talking about Dragonfly 44, a dark matter galaxy, a galaxy primarily made of dark matter. How many of these things do you guys think there are? Are these a common thing? Are they, you know, are they rare? What is their occurrence in the universe, do you suspect? Pieter, maybe we'll start with you.
Well, it's something that we don't quite know yet, but there's a flurry of papers that came out over the past year on this subject. Some by us, but a lot of them by other groups, and it seems they're actually surprisingly common. So they're not only found in the Coma Cluster, also in other galaxy clusters. And probably, well, almost certainly also in galaxy groups, perhaps even in isolated form, although none has been really confirmed to be completely isolated yet. So they seem to occur in all environments and are quite common. Alison Merritt, who's one of the graduate students operating the telescope and very much involved from the beginning with Dragonfly, has just published a paper where she found 4 of these diffuse objects in a galaxy group, which was very surprising and very exciting. So we used the Hubble Space Telescope to estimate the distances of those objects. And so it's very exciting because it's a new sort of, you know, basket of objects that is, you know, sort of a large things that are very faint, and we're only just learning about them.
Do you have any sense of
variety in them too? That they're not all the same, but some look a lot.
Variety in what way? And like the kind of stars, or their morphologies? What do you mean variety?
Some seem actually disturbed, like the morphology is not as nice and oval as Dragonfly 44, but there's clear distortions. One even looks like a U shape that we found in the galaxy group. So that one probably does not have a huge amount of dark matter because it's clearly not being kept together as Dragonfly 44 is. And so there's probably multiple ways to get a very big, very diffuse object. And we're only just learning about this entire class of things.
What about where do you have a sense of where these galaxies are in the evolutionary process? I mean, with elliptical galaxies, for example, they look like to me elliptical galaxies, very, you know, featureless, yellow. Are the stars in here old? I mean, you said there's globular clusters in there, so that would imply older stars. Do you got a sense of where they may be in the evolution of a galaxy?
So we have no clue, and that is incredibly exciting. Normally, you know, we quickly say, oh, okay, it's just that, or it fits in with this particular model, or it's something that had been predicted, or but in this case, I think everyone is scrambling to understand these things, and there's been 3 or 4 theory groups who have published papers, you know, saying what these things are, and I'm very happy to report that all 4 are completely different explanations for these things.
I'm one of the first people to admit that I find dark matter highly annoying. Not only because we don't know what it is, it won't interact with us in any way whatsoever, but I do know that it plays an important role in galaxy formations. But so do we know when galaxies collide, when they merge or they have interactions, and you've already said you don't know where this fits in the life cycle of a galaxy, but do we have any idea and this maybe not is about Dragonfly 44 so much, it's just about galaxy interactions in dark matter. Does it do anything to the dark matter? Can one galaxy strip all the dark matter away from another galaxy, or do we just not know yet?
Well, the general idea is that the dark matter interacts before the galaxies themselves interact, because it's so spread out. And that the dark matter actually helps galaxies come together. And so it's sort of a match.com, for galaxies. The dark matter begins to overlap, and that means the galaxies start to gravitationally interact. And then a process called dynamical friction will quickly bring the galaxies together, even though the stars are not yet touching, so to speak. And so the dark matter plays a large role in the mergers. And the thought is that the dark matter actually merges more easily and more quickly than the galaxies themselves do. So you can have a situation where the dark matter has already combined with the galaxies, and then the galaxies themselves are still spiraling around each other and then ultimately also merge. So there's some decoupling of the dark matter and the stars during the merger, is the thought. But mostly the idea is that the galaxies are just riding along with the dark matter, and the evolution of the dark matter halos in the universe drive most or maybe all of galaxy evolution.
As she always does, Carol read my mind. I was thinking of the bullet cluster when I asked that question. This is an interaction of galaxies where the blue stuff, which is dark matter, is being a little bit separated from the red stuff, which I believe is high temperature gas. If I'm saying it wrong, someone correct me. And you can see this sort of separation between this galaxy interaction this way.
It's also not just one cluster. It looks like it's two objects that have passed through each other. And so what happened was that the dark matter somehow interacted, whereas the stars and the galaxies in the clusters just passed through each other. So this was uncovered by a number of optical telescopes, including the Hubble Space Telescope, but the hot gas was revealed by Chandra in the X-ray.
Right. So that is okay. So let me it's getting close to. I'm running out of time. I want to get to some questions here. A lot of people on the live chat. I see Andrew Planet's been asking some questions. I'll get to that. Sarah Fox 21 has joined. Oh, Galaxia is here. Hi, Galaxia. Rainbow Panda has joined. So thank you guys for joining. Andrew Planet is commenting. You did this earlier in the Hangout about. The importance of eyeballs. He's saying that I just bought the book Night Sky with the Naked Eye, and yes, eyeballs count. At last, I'm learning the basics. Well, good for you, Andrew. The best way is just to go out and look up and start learning the constellations. That's what I did. So, and that's what I think is a good every skill everybody needs to have. Rainbow Panda's asking a really good question. How far away is the closest ultra diffuse galaxy? How far away is the closest one?
Yeah, that is an excellent question, and we're looking for ultra-diffuse galaxies that are as close to us as we can find them, because then we could study them in great detail. There's even the possibility, perhaps, that we could detect the dark matter annihilation signal if it exists, because these things are so massive. They might actually be good sites for that. The closest that we have found is about 20 megaparsecs away. There's also a few in the Virgo cluster at 16 megaparsecs that have been known for 40 years basically, but nobody paid much attention to them. So there's a few, literally like 3 in the Virgo cluster. Now there's also one that technically is an ultra diffuse galaxy in the local group. It's a galaxy called Andromeda 19. It's a satellite of the Andromeda galaxy, and that galaxy is being ripped apart by Andromeda. So it's a very
really. I did not know. So the local group, by the way, let's just say what that is. That is our personal group that the Milky Way is a part of.
Yeah, it's our backyard.
Galaxies.
Yeah, and so
wow. So that would be the closest then.
That would be technically the closest in terms of the size and its brightness. It fits in the category. Now that galaxy looks like it does, probably because of its unusual history, where the Andromeda galaxy is ripping it to pieces, and that stretches it out, which makes it look very big on the sky. And so, that's what makes it technically an ultra diffuse galaxy. It's not as large as the ultra-diffuse galaxy you have up here. Dragonfly 17 is about 3 times larger than Andromeda 19. And Andromeda 19 is basically a few clumps of stars that are stretched out a lot. But technically, that would be the closest ultra-diffuse galaxy.
So Andromeda does tend to affect its surroundings. I can see that. So yeah, really cool.
I think So part of the picture here is and this was alluded to earlier, right? Is that Dragonfly is exploring really this a region of the universe or parameter space of the universe that is very unexplored. Okay, so we're finding all sorts of things there. The Dragonfly 44 is awesome, but it's just the tip of the iceberg, right? We're going to be finding all sorts of weird and wonderful, unusual phenomena. And so even amongst the ultra-diffuse galaxies, right, it's not like there's likely to be one single explanation for it. So something like Dragonfly 44, you can measure its mean surface brightness and size and stuff, and it's likely to be something completely different than something like the nearby dwarf galaxy that's being ripped apart. In one case, it's probably a massive galaxy that for some reason failed to make a bunch of stars, and in the other case, it's a little wimpy dwarf galaxy that's just getting shredded. So I think it's just a new domain really in imaging. Where you're looking at a bit of the universe that nobody's ever looked at before, and we're just going to find a ton of new things.
Well, let's follow up on that a little bit more then. You said that when the way Dragonfly 44 was more or less discovered was when Peter had his blob dart going and he happened to catch something in the Coma Cluster that you were imaging. How are you using Dragonfly 44 in any kind of systematic way to find? Do you have a survey that you're doing? How are you using Dragonfly 44 to find these things you're describing?
Yeah. Okay. So right. So we are doing a survey, and the aforementioned wonderful grad student Allison Merritt. Okay. Her PhD thesis is largely motivated by exploring the outer halos of a systematic survey of nearby galaxies. And Peter mentioned that paper has just come out, and it's actually a very cool paper. It's as cool as Dragonfly 44, but we don't have time to talk about it. But, okay,
Carol, I see another hangout in our future.
There you go.
Sorry, I just want to say.
But what's fun about the Coma Cluster is it emerged through a completely different process, and the process was me and Peter basically chatting about how nobody really had looked at the Coma Cluster and explored its low surface brightness environment. So it was in some sense just curiosity is one interpretation of it. Lack of discipline is another. We just couldn't resist it. If you look at a Dragonfly, it's got this tremendous discovery potential. If you pointed at almost anything, there's a real chance you're going to find something new. And the Coma Cluster is so famous and so archetypal in terms of these massive galaxy clusters. We just could not resist looking at it. So the answer to your question is yes, we're doing a survey, but the Coma discoveries emerged, just out of curiosity. We just couldn't help ourselves.
And so this is being operated at observatories in New Mexico, you said, correct?
Yeah, New Mexico Skies Observatory is running.
Skies Observatories. And so as you find things that are interesting, follow-up observations are done by larger telescopes than like the Keck and Gemini North in this case. Okay, so we've got a couple of got another question from Hans Smiling or Hans Milling. When everything rushes together, it's hard to read it, right? But he's asking about the James Webb Space Telescope. Is it going to assist in studying these ultra-diffuse galaxies? And I guess by extension, does that mean, are these things very bright in the infrared, do you think? Because James Webb will be bright, will be an infrared telescope. Anybody want to comment on that? James Webb and studying these things?
Peter, you want to do it, or you want me to do it?
Any chance of using it?
There's a very specific thing that James Webb can do, we think, and that is study these globular clusters that we see in Dragonfly 44, these little points of light. They're simply too faint to take spectra of with any equipment that we have on Earth. James Webb has this wonderful spectrograph and integral field unit where these galaxies just fit in beautifully. So we might be able to measure the velocities of these globular clusters and study them with the James Webb Space Telescope. So I think follow-up studies for these very faint objects with James Webb, I think is an important, is a very good thing we can do. So it's the James Webb Space Telescope, as is the Hubble Space Telescope. They're more suitable for very compact things, for very small things, because they have such high spatial resolution. Luckily, we don't know why, but luckily these things have these compact star clusters. So they provide this additional tracer, and we can use James Webb to study them. I don't think James Webb will find a lot of new ones, simply because the field of view is so small.
Right, and it's not a survey telescope either, so it'll be pointing at specific things. So, good question though. Astro Bob is commenting, bummer, Amazon only has one in stock at 10K. Well, that's because these guys bought them all out. They probably don't have. Do you have any special relationship with Canon in making these telephoto lenses, Roberto? Or do you just...
Canon has been incredibly helpful in helping us realize this project. Whenever we have a technical question, we're able to refer to them, they come back with us with good information right away.
Well, because I'm a telescope nerd, I just got to ask you this: what kind of coatings are they? You said they had special coatings.
Yeah. So these coatings are just amazing, right? So they're these nanostructure coatings, sub-wavelength nanostructure coatings. So if you looked at these things, the coatings under an electron microscope.
You're talking about anti-reflection coatings?
Yeah, okay, that's right. So conventional coatings are really good, right? And can even for these even without these sub-wavelength coatings, these lenses have superb coatings. But this particular model has these sub-wavelength nanostructure coatings, which are just amazing, right? So if you
you're talking about over the visible spectrum mostly.
Yeah. So the way these things operate is kind of hard to explain. But if you look at these things under electron microscope, with an electron microscope, you'd see that you'd see like a grid of little pyramids. And so as the incoming wavefront comes through, it hits the tips of the pyramids and then propagates through to the base. And so it acts like a continuous variation in the index of refraction of the coating, which is the magic bullet for perfect optical coatings. So I don't know how Canon does it, but they have this secret technology, I guess, that lets them do this.
Tell us either, I'm sure.
Yeah, but they're just great. And so and this is the key to making Dragonfly efficient, right? It's terrific at getting down to low surface brightness levels, and that means handling the scattered light and the ghosting, and these lenses are particularly good for this.
Well, I have to say, most of the time you see these large aperture telescopes are generally reflective in nature, the elements that they put next to each other to make a bigger primary. I've not seen it done quite this way before. Yeah. That's always comes down to the cost of these refractors, guys. The number of optical elements, the quality of the optics, the optical glass, and the figuring, as well as the coatings, all figure into how expensive these are. And what was the diameter of those objectives? Do you know off the top of your head?
It's about 143 millimeters. So it's like
143 millimeters.
Yeah, 5.5 inches basically. The thing is, I love telescopes, and so I have all manner of telescopes. And sometimes you want a big reflecting telescope, and sometimes you want a refracting telescope. And depending on what you're trying to do, one or the other is the appropriate thing. But this, I must say, it's not a common thing to see, arrays of telephoto lenses. So I feel that this is a pretty innovative use of these lenses.
Well, I want to hear more about Dragonfly as you do more research. I'm hoping you guys will come back and do more hangouts. Maybe bring some of the grad students with you next time too, and we'll hear about the latest work you guys are doing. I want to thank you guys so much for taking the time out to talk to us. This has been an amazing hangout. We are out of time. I want to thank our sponsors, the Dot Space Domain Group. They, if you're interested in starting a website or blog in astronomy and space in space physics, please check them out. The link is in the description box. And thank you guys for sponsoring us. This is really helps put these on the air. I want to thank also the two AASs, American Astronomical and Astronautical Societies, and my good friend, Dr. Carol Christian. Hi, Carol. Thank you. And you managed to get the logo on your lower third. And so I'm going to put you up here as we sign off. All right. Thank you guys very much. And thank you all for watching. And as always, keep looking up.